And I'm working on midterm 2A from February 2019. I was asked to work backwards, forward, so that's what I'm going to do. And we want to see if this series converges or diverges. And we're going to start by representing this in summation form. And that'll be n factorial over 1 times 3 times 5, all the way up to 2n minus 1. And we're going to do the ratio test. If you see factorials or these running products, you do the ratio test. So we're going to take the limit as n goes to infinity of the n plus 1th term of the n over the nth term. And if that's less than 1, we converge, equal to 1, inconclusive, and greater than 1, diverge. And that's absolute convergence if we're less than 1. So we'll have the absolute value of n plus 1 factorial over 1 times 3 times 5 dot 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 2n minus 1. And then the n plus 1 term, we're going to replace n with n plus 1. So we'll have 2 times n plus 1 minus 1. And then we'll have n factorial downstairs, and 1 times 3 times 5 dot 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 2n minus 1. I don't know. We'll see. What does this become? 2n plus 2 minus 1, which is 2n plus 1. Yeah, I'm not sure that what you're proposing would be a simplification. I think most people would consider the double factorial to be more complicated. Okay, now I'm going to rewrite. I'm going to cross out what we see. We can go. These two can cross out. And I can write the n plus 1 factorial as n plus 1 times n factorial. And then at the bottom, all we have left is 2n plus 1 times n factorial. Okay, and these will cancel. So what is this limit going to give us? We have numerators polynomial degree 1, denominator same degree. So the limit as n goes to infinity is going to be the ratio of their leading coefficients, which is
1/2.
1/2, which is less than 1. So what's our conclusion?
Converges absolutely.
Converges absolutely by the ratio test. Okay. Questions? All right, how about this one? Okay, this is a pretty important problem. I love this problem. Okay, let's see if this series 10 minus sine n over n to the 4th is convergent or divergent. Okay, what do we know about sine?
Always between -1 and 1.
Right, it's between -1 and 1. So what can we say about 10 minus sine? If we have -1 here, we'll have 9. And if we have, I'm sorry, if we have 1 here, we'll have 9. If we have -1 here, we'll have 11, right? Does everybody agree with that?
Yes.
Okay, and then we have n to the 4th downstairs, so we can divide everybody by n to the 4th. Okay, now what is your hunch? Looking at this denominator, what is your hunch about this series?
But it will converge.
Converge.
Okay, since the denominator is n to the 4th, we suspect convergence. Okay, so if I want to use direct comparison test to show that our series, and this is a sub n, converges, we have to compare this to a b sub n that's what? Something larger that converges, right?
Right.
Yeah.
So what do we want to pick for our bn?
11 over n to the 4th.
11 over n to the 4th, because that's always going to be bigger and we know it converges. So bn let bn be 11 over n to the fourth, an is less than or equal to bn, and bn converges. So by direct comparison test, an also converges.
And also a quick question, just to recap, there's gonna be no FRQs, right?
No what?
No free response.
No free response, no. Okay, generalized P series with the Q value. Okay, certainly. Okay, I'll do that over here if you don't mind. 1 over n to the P log n to the Q. Okay, the summary. And you do need to know this because you will have a question. Yeah, we're working our way backwards from the end. That's what I was requested to do. What happens if P is greater than 1? Anybody want to tell me?
Converges.
Generalized.
Converges.
It's going to converge no matter what Q is. Okay. What happens if P is less than 1?
Diverge.
It's going to diverge no matter what Q is. What happens when P is equal to 1?
You have to check Q.
Okay. If Q is greater than 1, what's it going to do?
Converge.
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 And if Q is less than or equal to 1, what's it going to do?
Diverge.
Diverge.
Converge.
Okay. So let me put a red box around this and tell you how much I love the generalized p-test. Okay. Okay, tell me when you're ready for me to move on to part B.
Ready?
Okay. For part B, we want to use the alternating series error estimation theorem to figure out what is the error if we use only the first terms to approximate the sum of this series. Okay, if we only use the first 4 terms, the error bound is going to be the absolute value of the 5th term. Okay, and what is the 5th term? It's going to be the absolute value of -1 to the 5 over 2 plus 3 to the 5. Okay, which is 1 over 2 plus 3 to the 5. Okay, I'm not gonna, I'll be happy to do an integral test if we have time, but I was requested to work backwards from the end. Okay, you're gonna use it when your terms are positive, continuous, and decreasing. Okay, you might have to remind me. Okay, the next thing we're gonna do is sum these series. Okay, so we've got 2 series here. I can rewrite them. Does anybody know how we're going to tackle this first part?
Telescoping?
PF.
Telescope. We're going to write 1 over n squared plus 5n plus 6. Can we factor that?
Yes.
Yes.
3 and 2.
N plus
3, n plus 2.
2, n plus 3. And what do I have to do to make that a telescope?
You can do
Partial
PFD.
fraction decomposition. And we're going to do cover up for A and B. For A, I'm going to plug in -2 and cover up that denominator. So we'll get 1 over -2 plus 3, which is 1. For B, we're going to plug in -3 and plug in -3 and cover up that. So B will be -1. All right. So let's do the first one first. We're going to start with n equal 2, go all the way up to infinity, and we'll have 1 over n plus 2 minus 1 over n plus 3. And we're going to do telescope for that. We're going to take the limit as n goes to infinity. Starting with n equal 2, we'll have 1 over 4 minus 1 over 5, 1 over when n is 3, we'll have 1 over 5 minus 1 over 6, 1 over 6 minus 1 over 7. The ellipsis means keep going until we get to 1 over n plus 2 minus 1 over n plus 3. Okay, now we're going to cross out all the terms that cancel. What do we have left?
1 over 4 minus 1 over n plus 3.
Okay, and we're going to take the limit of that as it goes to infinity. 1 over 4 minus 1 over n plus 3. Where does this guy go?
0.
1 over 4. Oh,
0. So our limit will be 1 over 4. Okay. All right, I'll call that series A. Now we can work on B. So B, we have sum n equal 2 to infinity 5 over 4 to the n. And I can write that as 5 times 1/4 to the n. What kind of series is this?
Geometric.
Geometric.
Geometric. And let's check out the ratio. It's the absolute value 1/4 is less than 1. So we know it's going to converge. And what's the formula for the sum?
First term over 1 minus the rate.
First over 1 minus the ratio. And we need to be mindful of the starting index. I don't want anybody to miss this problem because they didn't use the right starting index. So that's going to be 5 times 1/4 to the power 2 over 1 minus 1/4. Word problems? You mean like the bouncing ball? No, there won't be any bouncing balls. Okay.
Yeah, so I kind of had a similar question. Sorry, I'm interrupting, but so there's going to be more problems kind of testing our ability to solve the actual summations and sequences than like testing our theoretical understanding, like the word problems like Brandon mentioned, or
I only remember one application problem. I don't remember any others.
okay, thank you.
Okay, the only sums you can find are telescope and geometric. No, only to determine, it can be negative or positive. That's why we use absolute values here. We just want that absolute value of the ratio to be less than 1 before we can sum it. Because if it's not less than 1, it's going to diverge. Okay?
I have a question.
Yeah.
What if the power is not just n, but something like 2n or 3n?
Oh, then
How does the formula change?
then you could write that if it's 1/4 to the 2n, you can write that as 1/16 to the n. And if it's 1 over 4 to the 3n, you can write that as 1 over 64 to the n. Okay?
Got it.
But
Thank you.
you'll rewrite it as something to the n. Okay, so back to our sum, we'll have 5 times 1 over 16 over 3 over 4. And that's 5 over 16 times 4 over 3, which is 5 over 12, right? Okay, so that's the sum for B. Now our total sum is going to be A plus B. Is going to be 1/4 plus 5 over 12. And that's going to be 3 over 12 plus 5 over 12, which is 8 over 12. And that's going to reduce to 2 over 3. Okay? All right, ready for the next one? Okay, you will need to know what these words mean: monotonic, bounded, increasing. Monotonic, bounded, yeah, you need to review your sequence definitions. Okay, what does it mean to be monotonic?
Going in one direction only.
Okay, it's going to be staying the same or increases, or stays the same or decreases. This is what it can't do. This. That's not monotonic. It can't go up and down. It's either doing something like this, increasing, or staying the same and decreasing, but it can't go up and down. That's what monotonic means, okay? And bounded means bounded from above and from below, okay? It has to converge if it's bounded and monotonic, that's correct. Okay, so let's think about a sequence that is neither monotonic nor bounded. That's going to be something that bounces back and forth between terms. And a good example of that would be n times the cosine of pi n. Because what this guy is going to do is going to oscillate between values that get bigger and bigger and bigger and bigger and bigger, okay? Because n's getting bigger, but cosine pi n is an alternator. Okay, so that would be neither monotonic nor bounded. What about something that's monotonic but unbounded? That's
How
the
about
simplest,
just n? Yeah.
that's the simplest thing I could think of. That's just going to keep getting bigger and bigger and bigger and bigger without bound. What about something that's not monotonic but bounded? Something that goes up and down all the time but never goes out of bounds.
-1 to the n.
Yeah, -1 to the n would be a good one. Or cosine n pi. Okay, it's always between -1 and 1, so it's bounded, but it's going up and down. Okay. What about something that's monotonic and bounded? Okay, this is always decreasing, and it is bounded. If you start with n equal 1, it's just gonna be bounded between 0 and 1, like that. Okay.
Could you also use arctan for this?
Yeah, arctan is always increasing. That's monotonic and it's bounded. Yeah, there are so many possibilities. These are the ones that I gave you were just one possibility. Okay. So infinite number of choices for all of these. Okay, now multiple choice. It does. Monotonic and bounded has to converge. And this is a sequence. The sequence converges. If it's a finite value in the limit, the sequence converges. The series doesn't. Yeah. The last question. You mean the one that we did before this one? What do you mean by last? Do you mean C? C or D? Which one? B, what do you mean by last series question? Is this the one you're talking about? You have to tell me, we're waiting on you. Are you talking about this one?
Maybe the one where we had the answer was 2/3.
Oh, is the one where we added the two together? From what, the beginning or the end? Oh, you got what you needed? Okay. Okay, this one is easy. They're telling us to use limit comparison. And we want to know which ones are convergent. Okay, so if we have sine or tangent and limit comparison and the argument is a function of n but not n itself, we're going to use bn as the argument to the sine or the tangent function. So that's easy to see for A, but bn is a little bit more difficult to see. What are we going to use for bn here?
1/n².
Right. It's not just 1/n, but we have sine cubed, so it's going to be 1/n times 1/n times 1/n, which is 1/n³. Now, we already know that this one does what? Divergence.
Diverge.
And this one does what?
Converge.
Okay, now let's do limit comparison. We'll have the limit as n goes to infinity, tan 1/n over 1/n. Okay, and if you saw the previous reviews, you know what I like to do is let t be 1/n, as n goes to infinity, t goes to 0. So we'll have the limit as t goes to 0 tan t over t. And that's going to be the limit as t goes to 0 sine t over cosine t times t. And that's going to give you 0 over 0, so we can use L'Hopital. So we'll have the limit as t goes to 0 cosine t over negative t sine t plus the cosine of t. And if you stick in 0, you'll get 1, which is finite. So what's our conclusion if you get a finite value here?
Both diverge.
Does what the other one does.
That means that AN and BN have similar growth rates. And that means that what BN does, AN does too. And BN diverges, so that means that AN diverges. Okay, so we know that AN diverges. If it were just tangent to them, what does tangent look like? Okay, that would be diverging due to having no friggin' idea what it does at end. Okay. Because you can't pin tangent down to a value. It'd be like oscillating, diverging by oscillating. Okay. You could do
There's a
test for
bunch of them.
divergence if it were just tan of them. Okay. Okay, so we know that A is not going to work. We can cross out all the ones that have A. And E doesn't work either because we know that A diverges. Okay, let's do this one next. Let me see if I have enough room here. If we do the limit as n goes to infinity, sine cubed of 1 over n over 1 over n cubed. We're going to let t be 1 over n cubed. Do our same trick here. Okay, so we'll have the limit as t goes to 0, sine t over t, sine t over t, sine t over t. And these are all going to 1 by L'Hopital, or if you just remember that result. Okay, so this is a finite value. AN and BN have similar growth. What BN does, AN does too. So in this case, AN does what?
Converge.
Converge. So B is the only one that works. Okay, the question is, if it gives us other trig value other than sine or tan, okay, it's probably going to diverge because suppose you have cosine. Okay. Okay, if you can do this by test for divergence. Okay, we can write that as the cosine of the limit as n goes to infinity. Okay, where's this limit going? If it goes to infinity, where's it going?
0.
0.
And so that's the cosine of 0, which is 1, which is not 0. So this is going to diverge by test for divergence. Okay. Now, I can't say in general what happens if it isn't sine or tangent. It depends on what it's the sine or tangent of. Okay. I would have to see the argument and other aspects of this series before I make a generalization. But I can tell you definitely, if you have sine or tangent of a function of n other than n itself, it's going to be limit comparison. That's the only thing I can tell you for sure. Okay. All right, are we ready for number 9? Okay, which of these Bn would give conditional convergence? That means when we've got the alternator, it converges by AST, but when you look at the absolute value, just the Bn part, it diverges.
In that one, we know the first one would be conditional, and then the second one, like we can see that it's kind of easy to see it's gonna converge if it's like just geometric. So, and since the answer is A, B, and C and D, then it's like just A.
Okay, well, if we know that these functions are decreasing, and the limit as n goes to infinity is 0, and they're positive terms, we know that AST will give us convergence. So we just need to look at these series. And we know from the generalized p-test, you said Bn divergence?
Yeah.
That's what you said. Does everybody agree that by the generalized p-test, this is going to diverge?
Yes.
So A is going to be conditional. Okay, for B, we can write this as 2 over e to the n. And the question as to what this does depends on this ratio. Is it less than 1?
Yeah.
Yes, it is, because e is around 2.7 something. So this one's going to be absolute convergence. Because if this ratio is less than 1, it's going to converge. Okay, this one, you look at the hierarchy of growth rates. Or if you got factorials or powers, what can we do here?
Ratio test.
We can do ratio test here. And we'll have n plus 2 factorial over n plus 1 factorial, n plus 1 to the n plus 1 over n to the n. And that's going to give us n plus 2 over n plus 1, and then we'll have n over n plus 1 to the n. Okay, that's because n plus 1 to the n plus 1 is n plus 1 to the n times n plus 1. Okay, now where is this ratio going as we go to infinity?
1.
That's going to 1. Anybody recognize this character?
Yeah, it's 1 over e.
1 over e.
That's 1 over e. So 1 over e is less than 1. This one will converge absolutely.
Can you go over all the forms that sort of thing can appear in? Because I know it can look different to be e and stuff.
Okay, 1 plus, what did he said? What was his formula? I don't use his formula. N plus b to the n. Was that the formula he gave us?
I think the b was before the n and the exponent, so it was like 1 plus a over n to the bn.
What lecture was that in?
I saw it in the review, the Broward Hall review.
I think it's less than 21. Oh, this is what he wrote on his paper. 1 plus, that's the way I wrote it, okay? So that's just going to give you e to the a, okay? So you see b is totally irrelevant, okay? So if we have 1 plus 1 over n to the n, that's going to be e. And if we have n over n plus 1 to the n, I can write that as 1 over 1 plus 1 over n to the n. And I can write that as 1 over 1 plus n to the negative n. And do you see the difference? This one has a positive power. This one has a negative power. What's this one going to give us?
E?
No, the powers are negative.
1 over e.
1 over e.
1 over e, exactly. And what if I had 1 plus 2 over n to the negative n? What would that be?
2 over e.
2 over e, you got it. Okay. Okay, so we said conditional for the first, absolute for the second. And what's the third one? This should be less than 1, I'm sorry. The third one, 1 over e is less than 1, so that's absolute. So which one converges conditionally? Only the first one, right? Only this one. Okay, so number 10, let's suppose h is less than f and f is less than g, and everybody is non-negative for all x greater than 1, and all these functions are continuous and decreasing. These conditions apply for the integral test. So which one is going to guarantee that f converges?
The ones that are equal to and greater.
That's right, only the ones that are greater than or equal to. So that'll be what? This one is greater,
And B.
and this one is a reasonable facsimile. Okay, the smaller one converging doesn't tell us anything. Okay, can we move on? I had some questions about this one, and we want to know what k will allow this to converge. So what you need to do is examine the highest power in the numerator and the highest power in the denominator, because those two guys are going to determine the behavior of this series. And we can rewrite that. We can say that n to the 1/4 over the square root of n to the k plus 9n is going to behave similarly like, and this squiggly means similar to. We can write that as n to the 1/4 over, I can write this in rational exponent form as n to the k over 2. Okay, does everybody see that? This power on n is n to the k over 2, because that's a square root. Now, I want to write this like a p series, so I'm going to write this as 1 over n to the k over 2 minus 1/4. Okay? Now, remember for the p series, what does this power need to be for convergence?
Greater than 1.
Right, p series k over 2 minus 1/4 has to be greater than 1. So we're just going to solve that inequality. I'll add 1/4 to both sides. So k over 2 is going to be 4 over 4 plus 1 over 4, which is 5 over 4. And if I multiply both sides by 2, that should be greater than. Greater than. If I multiply both sides of this inequality by 2, we'll get that k is greater than 10 over 4, which is 5 over 2. Now, how do we write that result in interval notation? K is a member of 5 over 2, not including to infinity. So any k 5 over 2 that's greater than 5 over 2 will work. Strictly greater than, so we'll pick the first option.
How did you know to do the k over 2 minus 1/4?
Okay, because we want to make this look like a p series. What does the p series look like? It's 1 over n to the p, right?
Yeah.
So we want to make it look like that. Okay, are we ready for number 6? I think I need to do these on
So
a.
did you sorry for that one? Did you just put the into the 1/4 on the bottom in order to have that
Yeah,
minus?
remember, x cubed is the same as 1 over x to the negative 3. Do you agree with that?
Mm.
That's all I did here. E is an element of, okay. Oh, you need to know interval notation. Yes. This means not included. This means included. All right. So strictly greater than, you use the open, greater than or equal to, you use closed. Okay. Yeah, you might see interval. I don't know. I can't remember. Okay, are we ready for number 6? Which is true for the series. Okay, if we look at A, we see this rational function raised to the power k squared. What test does that suggest?
Root.
The root test.
Root. Okay, so let's see if A is going to work with the root test. We're going to take the limit as n goes to infinity, k over k plus 1 to the k squared, the absolute value. Oh, that's n. Ugh, I'll put a k here to make it consistent. Okay, and they're all positive, so we can write this as the limit as k goes to infinity. K times k over k will just give us something to the k. And that's going to give us k over k plus 1 to the k. That is our very good friend. Who knows what this is?
1
1
over
over E.
Right, that's going to be 1 over e. All right, it's less than 1, so does this series converge or diverge?
Converge.
It converges absolutely by the root test. Okay, for B we have factorials. Which test does that suggest?
Ratio.
Ratio. And so we'll have sum k1 to infinity k factorial squared over 2k factorial. So we're going to replace every instance of k with k plus 1. We'll have k plus 1 factorial quantity squared over k factorial squared. In the bottom, we'll have 2 times k plus 1 factorial and 2k quantity factorial. And we need to take the absolute values of those. Okay, that's the shortcut. If it's on top, replace it with k plus 1. If it's on the bottom, replace it with k plus 1. And then the bottom of this will be the k instance, and the top of this will be the k instance. That's a shortcut. Okay, now let me write this out so that we can see what's happening. We'll put a little detail in here, and we don't need the absolute values because there's no alternator. There's no alternator or negative terms. So this will be k plus 1 times k factorial times k plus 1 times k factorial. That's what we get from this guy. And downstairs, we have k factorial, k factorial. Okay, upstairs we have 2k factorial, and downstairs we have 2k plus 2 factorial. And let's clean this up a little bit. That's a lot of cancellations, isn't it? Okay, I still need to simplify this one. So we'll have k plus 1 times k plus 1, and then we'll have 2k factorial upstairs. Downstairs, we'll have 2k plus 2 times 2k plus 1 times 2k factorial. And these two will cancel. So we're left with a polynomial degree 1 on top and a polynomial degree 1 on the bottom. The limit as n goes to infinity is going to be the ratio of the leading coefficient, which is
1/4.
1/4, which is less than 1. So this converges absolutely by the ratio test. By the way, what's your favorite test?
Ratio.
Everybody's favorite is the ratio. Okay, I knew you were going to say ratio. Okay, how many of these statements are true if this series has positive COVID ratio till I die? COVID test is your favorite. Okay, funny. Have you been tested? It hurts. They stick a gigantic swab all the way up to your nostril until it touches your brain 4 times. It really hurts. Okay, positive terms. Which of these are true? If the limit as n goes to infinity, a sub n plus 1 over a sub n equal 1, is this true?
No.
No.
Test, it means ratio test is inconclusive. Not that the series converges conditionally. What about this?
Also inconclusive.
That would be
This
TFD.
doesn't tell us anything about the series. This tells us that TFD is inconclusive. Okay, what about the root test? If the root test gives us a 0 in the limit,
That's true.
this is absolutely true. Okay. What about this one? If the root test gives us a 0, does that tell us divergence?
Inconclusive.
No, that's inconclusive. So the only one that's true is this one. All right, what did you want here? Okay, I don't remember. What did we say? We said that the first one converges absolutely by the root test, and the second one converges absolutely by the ratio test, okay? I think the work is more important than the, did you get the work for these? That's what I care about. Yeah, okay. All right, we're down to the first page. And we do have problem for an integral test. Yay, we have time for an integral test. Okay, which of these will diverge for the using test for divergence? And that means what we're looking for is the limit as n goes to infinity of a sub n is not equal to 0. That's what tells us divergence for TFD. Okay, now remember the hierarchy of growth rates. Let me write it down here. The log of n to the p doesn't grow as fast as n to the q, doesn't grow as fast as a to the n, doesn't grow as fast as n factorial, doesn't grow as fast as n to the n. So number 7 for a second. Okay, so we can just look at the hierarchy of growth rates, and here P and Q are positive. A is greater than 1. Okay, so we can look. N grows faster than log, so the limit as n goes to infinity, the log of n over n gives us what?
0.
0. So this is inconclusive by TFD. That's not the answer. What about this one?
Log of 3/4.
Right, the log as n goes to infinity, the limit as n goes to infinity of the log of this stuff, that's the same as the log of the limit of this polynomial over a polynomial that has the same degree. And you know this limit's going to be 3/4. So the log of 3/4 is not 0. So does this show us divergence by the test for divergence? Yes.
Yeah.
Yes. So B is a yes. Okay, what about C?
Also inconclusive.
It's telescoping.
Yeah, but by TFD it would be like 0 minus 0.
By TFD, it would be 0 minus 0. I was thinking we could do telescope to know for sure. Also inconclusive. All right, what about this one?
1.
Yeah, 1 over 2 minus the cosine of 1 over n. That's going to be 1 over 2 minus 1, which is 1, which is not 0. Okay, so the only ones that will show us divergence by that test are B and D. Okay, what about absolute convergence? Okay,
In the first one,
go ahead.
in the first one, using the ratio test, we get the limit goes to 0, so it would be at least conditionally convergent.
Did you do the ratio? I would do the root test because we have an e to the n. I think I want another piece of paper for that one. Okay, first of all, yeah, if we want to know about absolute convergence, we're going to drop the alternator. So we're just going to examine this right here. The positive part, e to the n, over n factorial to the 1/2. And I'll do the root test for this because we have e to the n, and we'll have the limit as n goes to infinity of e to the n over n factorial to the 1/2 to the 1 over n. Okay. And that's going to be the limit as n goes to infinity, e to the n to the 1 over n. That's just going to give us just plain e on top. On the bottom, we'll have n factorial to the 1/2 to the n. And that's like the 1 over n, sorry. So that's like the nth root of n factorial to the 1/2. Now, does anybody remember what I said about this limit? The n factorial to 1 over n. What's that limit? Infinity. Infinity. Okay, this is what you need to remember. It's like a bit beyond the scope of the course to show you why. I posted a link to why this is true. There was some discussion on one of those technical websites. Okay, so basically we're going to e over the square root of infinity, which is what?
0.
That's going to give us 0 because the bottom goes faster than the top. What's our conclusion here?
Convergence absolutely.
Absolute convergence.
So that was gonna be one of my questions. If we have n to the n or n factorial, which are all like above in the hierarchy,
Okay,
they're not affected by any exponents, right?
here's our hierarchy, log. Okay, if you raise these to the 1 over n, how am I going to write that?
Log of
That's going to give you 1. The next one in line is n to the q. N to the q to the 1 over n is going to give you 1. The next one is a to the n. That's going to give you just a, right?
Yeah.
Okay, it's the ones that grow faster than exponential that go to infinity.
Mhm.
The answer to this one,
Maybe
no.
for example,
This is really a bit beyond your comprehension to know that this is true. That's why I just gave you this fact, just in case you should see it on the exam.
but I mean, in terms of growth rates, e to the n would still grow slower than n factorial to the square root of n factorial.
E to the n is in this category. All right, so let me finish. So these are all constant. The next two are going to be infinite. N factorial to the 1 over n gives you infinity. And so does this one, of course, n to the n to the 1 over n will give you n, which is going to infinity, okay? So if you can remember using the hierarchy of growth rates, that might be helpful. Now, I would not expect you to figure this out on your own. We just give it to you. I hope that answers your question. I'm afraid that sometimes he puts this stuff in without having explained it because he forgets that he hasn't explained it. So I wanted to make sure you guys got this. Okay.
Sorry, for the second line, n to the q.
Yeah, that's a q, not a,
Is it to the 1/2?
yeah.
But then is it to the 1/2 or to the 1?
It should be 1 over n. I'm sorry.
Okay.
It was 1/2 over here. Thank you for
Thank you.
correcting. All right, what's next?
Can you go back to that for a second?
Yeah.
I'm good, thanks.
Okay, so we still have to do this guy. All right, they're trying to trick you here because for this one, we know that the sign of n is going to be trapped between -1 and 1 no matter what. Yeah, 0 is a finite value. LCT yielding 0, that's definitely a finite value. Okay. That means that whatever Bn does, An does it too. Okay, so if we stick in factorial there, does that change our bounds on sign?
No.
No, it's still going to be -1 to 1. Okay, so our numerator, 2 minus the sign of n factorial, what's that going to be bound by?
1 and 3.
1 and 3. Okay, now look at our denominator. That's going to go like 1 over n to the 1/3. Is that going to converge or diverge?
Diverge.
That's a divergent P series. So if we want to show that something diverges, and my hunch is that the series will diverge because of the denominator, we want to show that this is bigger than something that diverges. So what are we going to use for Bn?
3 over n.
We want to show that this is bigger than something that diverges.
1.
Oh, 1.
We're going to use let Bn be 1 over n to the 1/3. And An is greater than Bn. Bn diverges, and that means that An diverges too by direct comparison. So this one converges absolutely, and this one diverges.
If the sign was squared, it will be from 0 to 1, right?
If the sign were squared, yeah.
Okay.
0 to 1. Okay, this one, we didn't cover this, so I'm going to skip it because somebody asked for integral test. Okay, and which one of these can you find the sums for? Remember, we can only find sums 2 ways: telescope
And geometric.
and geometric, if the ratio is less than 1. So which one of these qualify?
P and R.
R.
Yeah, we could do PFD on this and then telescope. And this one is a geo series. All right. Okay, now let me do an integral test for you and then we'll be done because I have another class at 4. So let's say we have sum n equal 0 to infinity. 3n e to the -n squared. Okay. And I want to know. Oh, okay. For geo, if the ratio, if the absolute value of the ratio is less than 1, the limit as n goes to infinity of r to the n is 0. Okay. The limit will go to 0 when the ratio is less than 1. That's just a constant. These are both just constants. And you can put them in front of the series. The ratio here is 1 over e. That's equal to √3 over pi sum n equal 2 to infinity 1 over e to the n. Okay. Can you take a picture of it? Because I really need to move on. Got another class after this, and I still want to show you one more thing. Okay. There's no limit that I know of. Okay, let's do ratio test. So integral test is 3n over e to the n squared. And it's positive, decreasing, and continuous. We've got those 3 conditions for integral test. So we're going to see what happens to the integral 3x e to the -x squared dx. Okay, how am I going to integrate? What am I going to do here?
U sub.
Yeah, we're
sub
gonna let u be negative x squared. So what's du?
minus 2
Negative
dx.
2x dx. That means that dx is du over negative 2x. And so let's pretend we have an indefinite integral. We'll have 3x e to the u, and dx becomes du over negative 2x. So that these two x's will cancel, right? So I'm going to pull out the negative 3 over 2. And what is this integral? That's pretty easy, right?
EU.
That's going to be negative 3 over t e to the u plus c. And that's going to be negative 3 over t to e to the negative x squared. And now we want to evaluate this between 0 and infinity. So I'm going to write this as negative 3 over 2, the limit as t goes to infinity, 1 over e to the t squared minus 1 over e to the 0. Okay, and where is this going? If t is going to infinity, the denominator goes to infinity, and this quantity goes where?
0
0. And what's this quantity?
goes to
1.
1. Okay, so we have negative 3 over 2 times negative 1, which is 3 over 2. Okay, so we're doing integral test. What does this tell us? This is
If
a
it's finite, it'll converge.
if the integral is finite, that means the series converges. Okay, so that's integral test. Your terms
But
have
we
to
cannot
be.
tell.
Say again.
We cannot tell if it converges absolutely or conditionally, right?
Oh, we've got only positive terms here, so this would be absolute convergence.
Okay.
Because somebody asked me to do an integral test. So I did this one using the integral test. You could also do this using the root test.
Could you clarify again why that's absolute convergence?
Because it's a positive terms only and it converges. Remember? If the absolute value of convergence, AN converges absolutely. Remember that statement?
So if we're given like a series that doesn't have an alternator and it converges, then it will converge absolutely.
That's absolute convergence, yes.
Okay.
I don't remember exactly how many questions. Yeah, it's in the neighborhood of 20, but some of them have multiple parts, so I don't think it helps you to know how many questions. I mean, I don't know how many actual parts are involved. Some of them have 3 parts, some of them have 4 parts. Okay, I have to go. Thank you for coming. I hope you knock them dead, okay? Good luck to all of you. Thank you so much for staying and paying attention.
Thank you so much.
Okay, make me happy. I don't want to cry, so make sure you don't make me cry. Okay, bye.